The next talk will be by Johannes on the effective theory of medium-induced radiation.
Yes, so my name is Johannes and I'm a PhD student of Conrad in Bergen. And this talk is about what is called an effective theory of medium-induced radiation. And it's from a paper that me and Conrad and Adam wrote, and we just put it on archive last week. Yeah, so just starting with some simple stuff, Jack quenching. So when you smash these particles together, you get the quark-gluon plasma. And sometimes you get a hard collision and you get highly virtual particle, and this will radiate and create a jet, as you can see here. But of course, when you're in the quark-gluon plasma, this medium will interact with it and it will modify the jet, and that's jet quenching. And so as these particles go through the quark-gluon plasma, they can experience like many effects, but for example, transverse momentum broadening, can be elastic collision with medium constituents, and also radiation. And today I'm going to talk about medium-induced radiation. So as the particles go through the medium, they scatter with the medium constituents, and these scatterings induce emissions. And if these emissions go outside of the jet cone, it leads to energy loss. So these are quite important. Exactly, they are the dominant contribution to energy loss in light quarks and gluons. So you can think of it as kind of this picture here, that you have one particle with energy E, and then it splits several times, and it ends up with, well, you get, in the end, you get a distribution with particles of energy XE, where X is this energy fraction. But of course, we actually want to calculate these things. We don't just want to draw a picture, but we need some numbers here. And what we need then is to put numbers on each of these splittings, and you can put it on this plane here, which is omega, the energy and time plane. But we need to know this function to describe these points. So therefore, we need to zoom in into one of these splittings, and we will calculate the emission spectrum for each of them. So, and this was also mentioned by Carlotta. We are going to talk about the same thing, the emission spectrum, and it's given by this formula here. And as you can see, there is this subtracted term here, and that's the vacuum. The K0 is the K0 is the vacuum. So we only care about medium induced emissions, so therefore we subtract this. And as you can see, so basically here there's an illustration of what's going on. So we have a parton, and it interacts with the medium, and this leads to an emission of a gluon. So the difficult part of solving this is actually this K thing here, and it's you can see it on this illustration. So here in this line is in the amplitude, and here it's the gluon is emitted at time t1, and in the complex conjugate amplitude it's emitted at t2. And so the thing that's going on in between here is this K, and it's mathematically it can be solved. Is the solution to this Schrödinger equation here, where this V is the scattering potential. And yeah, the bad thing about this though is that it's in general you can only do this numerically, and analytic solutions. Then if you want analytic solutions of this, then you have to use some approximation. And so I'm just going to talk a little bit about how this is normally done. So the first thing you can do is something called the opacity expansion, where you expand this K in the numbers of scatterings with the medium. So first, the full K is kind of like equal to the vacuum times the vacuum with one splitting, and then with two splittings, and so on. Then you have to truncate this at a finite order, so you don't get an arbitrary amount of splittings. The other way to solve this is the harmonic oscillator approximation, and for soft scatterings you can approximate this potential V here as just Q hat, the jet quenching parameter, times x squared. So this is just harmonic oscillator, and then you can be solved exactly to all orders, which is quite remarkable. The bad thing though is that none of these methods give satisfying result in the whole phase space. That means that you can't use this for every single emission. But what we just find out in our paper is that you can combine 3 expansions, namely the opacity expansion, something called resummed opacity expansion, and the improved opacity expansion. And if you combine these 3, you can get a good approximation of this emission spectrum in the whole phase space. And of course, we didn't invent all of this, we have to say. Opacity expansion has been known for a long time. Improved opacity expansion is something that was developed in recent years by Yassin, Conrad, and Joao and Alba. And this resummed opacity expansion is also, as Carlotta said, they also did it in her paper, but only in like, she mentioned it as like a low energy limit of the emission spectrum. However, what we did in our paper is giving this more like a formal approach, like a formal derivation. So I'm going to start with the opacity expansion, and as I said earlier, it's just you expand in scatterings around the vacuum solution. So you have the vacuum K0, and then you have a scattering V here. And this scattering potential V contains both a real and a virtual part. And the difference between that is that the real part, then you actually, the momentum here will change, but in the virtual part, the momentum will not change. So that's the difference. And if you do this, if you calculate this, then you get an emission spectrum, and you can see that here we get an energy scale omega c bar, which depends on the length of the medium or time. And we calculated this to the first and second order. So as you can see here, and these are the soft and hard limits. And what you can see at low energy, the spectrum goes as L over lambda, where L is the medium length and lambda is the mean free path. So you expect this to converge only when this is small, because this is here you have L over lambda to the first, and here you have L over lambda to the second. So if this L is bigger than lambda, then this grows, and you don't expect convergence. However, in the high energy, you actually don't get this L over lambda, but you get L over lambda times omega c bar over omega, which is also Q hat 0 times L squared over omega. And so even though you actually just expect it to converge when L over lambda is small, you can see that in high energy, it also can converges if the energy is bigger than Q hat 0 over L squared. So to illustrate this, it's probably easier to see on a picture. So the opacity expansion is valid for early times, when L time is smaller than lambda, but also for high energy, which is quite interesting. So we draw this region of convergence on this plane here, and we also, of course, calculate this emission spectrum for 4 different times. So, and we also here we compare to the numerical solution that Carlotta was talking about earlier, and you can see that at the early times, which is like down in here, this area, and this green curve here, it matches almost perfectly. But at later times, you see that it matches for high energy, but here at some low energy, it starts to move away from the dashed curve, which is the numerical solution. And here at even higher energies, when even later times, I mean, you're up here somewhere, so you only expect it to work for just this little part here. And you can see that the same thing, that it works well here at high energies, but then it fails at some point, and it fails very badly, as you can see on this. Okay, so the thing is that we need something that works in this area. So now we have something that works for early times and at low high energies, but we need something that works here. So that leads us to the next expansion, which is the resummed opacity expansion. So the difference between these 2 expansions is that you only expand in real scatterings. And I talked about, like, as I mentioned before, the real scatterings, they change the energy, they change the momentum, I mean, in the scattering. And all the virtual scatterings that don't change momentum, they are now resummed in this pseudo factor here. So you can see that now in the same expansion, you have the vacuum but here it used to be a V, but now it's a sigma, which is only the real term, and you have the pseudo-cov in front. So that's the difference. For short media, it's kind of interesting. There is some opacity expansion just becomes the normal opacity expansion. However, it's very interesting that this actually works for longer media when L is bigger than the mean free path. And here you get a new constant that we call omega beta Heitler, because like in very low energies, you're in the beta Heitler regime. And we also calculated, of course, the emission spectrum in this case for when L is bigger than lambda. And as you can see, for low energy, for very low energies, the first term here is leading, so we expect it to converge since the first term is bigger than the second term. However, at higher energies, you can see that these terms are actually the same. So it's you won't expect it to converge there. I mean, it could, but there's no sign of it. So to sum up the resound opacity expansion, it's valid down here. It's the same as the opacity expansion because they are the same here. But the good thing is that it also is valid for energies below the beta Heitler regime. And you can see this on this plot. So, but now it only matches the numerical solution for very low energies. And it's also, I don't know if you can see it, but here we actually plotted the first, only the first term and the first and the second term. And you can see that the first term kind of goes away from the numerical solution as you approach omega beta Heitler. But this, if you include the second term as well, it matches very well all the way up to omega beta Heitler. So this is points to that if you include more terms in your expansions, it can like be systematically improved in that way. But we still haven't got anything that works in this region, which leads us to the next expansion, which is the improved opacity expansion. And you get this from manipulating the scattering potential. So you write it in two different terms, and the first term is just the harmonic oscillator term that I talked about before. And as I said, the harmonic oscillator is an expansion in many soft scatterings. As you can see here, you have many soft scatterings, and then you have an emission. And as I said, also it can be solved exactly. However, it can only create emissions up to an energy scale omega c, where you have the q hat and L squared. So if you want emissions with energy above this scale, then you need to include harder scatterings, and that leads us to the improved opacity expansion, which is an expansions in hard scattering around the harmonic oscillator solution. So now this K, that here you used to have the vacuum, but now you have the harmonic oscillator solution, and then you have this delta B, which includes harder scatterings. So with the improved opacity expansion, you can go to even higher energies than omega c, and you can see it kind of on the side here that you have. I don't know if you can see it, but you have soft scatterings, then you have one hard scattering, basically. So a little bit more about the improved opacity expansion. So I saw in the last slide, you saw Q hat, and it's written in terms of this matching scale Q that you need to introduce to get to the improved opacity expansion. And so the question is, how do you actually choose this Q? Well, it was in a paper by Joao and Yassine, they show that you have to choose it in this way. So these two equations, they now provide an equation for Q in terms of energy. For Q hat, I mean, in terms of energy. So now Q hat runs with energy. But this running breaks down around the beta Heitler energy. So the whole point of this whole thing is to say that the improved opacity expansion kind of does not work for energies below the beta Heitler, because this running of Q hat breaks down at that point. Of course, we calculated emission spectrum for the improved opacity expansion as well. And for here, this is the soft limit. So for lower energies, the harmonic oscillator contribution dominates. However, at higher energies, this next to harmonic oscillator contribution is actually much bigger than the harmonic oscillator. So to get the correct result at higher energies, you need to include this harder scattering. And also, it's interesting to note that this term here is just the same high energy limit as the opacity expansion that we talked about before. So how does this look on this plane? So we can draw it like this. So in this area, for energies lower than omega c, the harmonic oscillator is valid. However, in this high energy regime here, then you have to use the improved opacity expansion or the opacity expansions, because they kind of go to the same formula here. And as I was saying, this expansion breaks down at omega beta Heitler. So here you can't use this. And again, you compare this to the numerical solution from Carlotta and Fabio, and you see that they match. It actually matches very well, almost for all energies here. But again, you can see that something happens at very low energies, which is also what we expect. It doesn't really work here. So I'm just going to summarize a little bit now. 10 minutes, okay. Yes. So at very early times, so you only need to include few scatterings that will induce emissions. There can be few soft or few hard scatterings, and this is covered by the opacity expansion and the resummed opacity expansion. However, in this middle regime here, you have to use so all three possible processes kind of contribute here. So you have this very soft beta Heitler emissions, which you get from the resound opacity expansion. You have this multiple coherent scattering regime, which is given by the harmonic oscillator, and here you have this hard regime where you can use the opacity expansion or the improved opacity expansion. At late times, you can see that this green part goes away, and you only have to use you only have this beta Heitler regime and this harmonic oscillator regime left. And also, like naturally from the expansion, when you do these calculations, you just get out these energy scales: omega c bar, omega beta Heitler, and omega c. And you can see that these three energy scales kind of divide these regions. So now I'm going to show the full solution. So if you combine the ROE and the IOE, and we used so we combine these two, and we use, but they're not exactly they don't exactly match at the transition points. We have to use this smoothing function at the transition point, which is here. Then we get the full solution, which is this full line here, and it's compared to the numerical solution, which is this dashed line. And as you saw also on Carlotta's plot earlier, it actually matches very well, except for around this transition point where there is a little bit of error still. But we expect that if you go to higher orders of the expansion around these transition points, then this error becomes smaller and smaller. So, and the last part of my talk, I'm just going to talk about multiple emissions. So when the multiplicity here, if you integrate over this emission spectrum, when this is large, then you have to take into account that you can have multiple emissions. But if you check this for small media, this multiplicity is small, so you actually don't need to take into account multiple emissions. However, for big media, you can see, if you do the maths, you can see that the multiplicity of the harmonic oscillator emissions actually get big here. So here you have to take into account many harmonic oscillator emissions. And the way you do this, well, one way to do this is to define this energy distribution, which is kind of what I explained in the beginning. You have this energy, one parton with energy E, and it splits arbitrarily many times. And in the end, you get many partons, and they have energy XE. So you want to end this distribution of this energies here after a certain time t. And one way to solve this is through a rate equation like this. So basically you have this energy distribution D, and you take into account one splitting. It's like a differential equation. So at one time step, it's the same, but with an extra splitting. And this splitting rate P that is the splitting is just basically, it just comes from the emission spectrum that I've been talking about the whole talk. So we solve this numerically with our kernel that and we get this. So for early times, you can see that, of course, when there was only one parton, the full peak is here at 1. It's just a delta function at 1. So here is at early times, this peak is still there, but it has some energy has been moved to softer modes. And as you can see, as time goes, more and more energy will go away from the peak here and go to softer modes. And in the end, this is dominated by this harmonic oscillator splittings that is very effective at transporting the energy from this area to the softer modes in this area. We also tried to solve this analytically, and you can do this in a few different ways. And the simplest thing to do is just you have one single emission basically that and that's it. And it kind of works at early times because you don't have time for that many emissions at early times. So you only have time for one basically. And then you have the pure harmonic oscillator solution D0, which also you can solve exactly. And that works kind of okay at late times because at late times everything is dominated by the harmonic oscillator emissions. And then we also made this kind of mixture thing where you have an harmonic oscillator solution, but you add one hard scattering, and it gives you like a little mix where it follows this early time behavior, but at the late times it goes to the harmonic oscillator behavior. So I will just summarize this and compare this. So at early times there are very few emissions, and the spectrum is not modified that much. And you can see actually when comparing this numeric curve here and this analytic curve that it looks qualitatively very similar. So it works kind of well to only expand in one emission in the beginning. However, at intermediate times, you can see that harmonic oscillator emissions become important. And so more energy is transported from the hard sector here to the soft modes. But there is still some residue of this early time behavior. And also you can see that this mixture solution, the D0 plus this one hard splitting, it gives you like qualitatively a good match to the actual curve here. At late times, as I said, the harmonic oscillator emissions dominate, and you get a large modification to the distribution. So this peak basically disappears, and you get just these softer modes. And here it's interesting to see that the beta Heitler emissions become important. So this dashed curve that you can't really see that well is if you don't take into account the beta Heitler regime. So then it's pretty flat. 2 minutes. But if you take into account the beta Heitler regime, then you get like you get more of the soft modes basically. And yes, I'm just going to say that in this analytic solutions, we didn't actually include the beta Heitler regime, so that's why it doesn't match at very low energies. So that brings me to the conclusion. So I call the talk an effective theory for medium-induced energy spectrum. And I mean, it's you can discuss whether it's good to say like an effective theory, but I would say that it's you could kind of say it because you have a very complicated problem that you have to solve numerically. But what we did is that we put it into different we kind of divided up the problem where each solution in these different regions that we divided up in is much simpler. So so basically you take a very hard problem and you make it simpler in different regions, and that's why we call it an effective theory. And we have a good theoretical understanding and control in these regimes. And it's also improvable order by order, which means that if you take more and more emissions scatterings into account, higher and higher ordering scatterings, then you get to a better precision, basically. And as I said, this is done through the opacity expansion, the resummation opacity expansion, and the improved opacity expansion. And you get these 3 energy scales that divide them up. Also, as I said, you have to take into account multiple emissions, and this can be done through a rate equation, which I showed. And it kind of gives you a better understanding of how this jet kind of evolves in time. But of course, this is not the whole thing. We have, for example, if you want to actually compare it to real world data, you need to incorporate the vacuum or the transfer momentum. And we will probably work on this, I guess, in the future. Thank you.
Now we have time for questions.
So for the multiple emission, you still probably have just to use the simple resummation, right? Each emission you consider, is independent of the next emission.
Yes,
right?
yes.
Okay.
Yes.
Maybe another question is, maybe I think all of us have probably not considered this carefully. So far, a lot of people, including you, are focusing on just you looking at a single parton spectrum, all the, including multi-emission, including all this interference effect. Have you ever considered whether you can look at like 2 parton correlation function? In particular, their angular correlation, their energy correlation. That will actually, what we find out in a simple case, that will actually provide a lot of information about the space-time picture of the emission. Mm-hmm. If you look at the 2-parton correlation, for example.
Yeah, that's definitely very interesting and something to look into.
Yeah,
more detail.
Maybe for during the discussion, this week we can maybe one afternoon we can focus on this.
Hi, Johannes. Thank you very much for the nice talk. Actually, I have a question on your plot with all the expansions. I think it's slide 14. So I realized yesterday that for the low energy regime in that plot, you use just the first order in the resummation opacity expansion. So basically you use our low omega formula. And I was wondering why you use only the first order and not the second that you have already computed. And if it does improve the transition between the 2 regimes at the Wetterheiler.
Yes, that's definitely a valid question. We could definitely have used both orders and it would improve it. As you can see on the other plots, it actually does improve it. I think the reason we only included the first order here is because this is what we use to solve the rate equation. There we have all the limits in a much simpler way. So if we wanted to include a second order, it would take much more time, basically. But yes, you could do it.
Okay, and maybe following question is, how do you really do the transition? Because if I recall correct from Jacin's paper, the opacity expansion has no solution below 2e omega Wetterheiler or something like that, and the other one is the improved opacity expansion, sorry. And the other one goes up to the Wetterheiler. So how do you do this transition? Is just interpolating or?
Yes, so they don't match perfectly at that point. So you have to make some interpolation
function.
Okay, yes.
Thank you.
Thanks for the talk. So in the resummation opacity expansion, you use this trick of resumming the virtual diagrams in a pseudocofactor. Could you use the same trick for the improved opacity expansion? So you rewrite it with a pseudocofactor with virtual diagrams, and would that allow you to get into the Wetterheiler regime, or is that?
That's a good question. Actually, I have kind of tried it, and it's not trivial, but it might be able to be done, basically. I tried a little bit and then I gave up, but maybe I should try some more.
Okay, thanks.
Any other questions? Any questions from online? You can raise your hand. Okay, so if not, then let's thank Johannes again.